Hello everyone. So the purpose of this video is to lay out a rigorous framework for quantum mechanics and really put an emphasis on trying to build an intuition of why we're doing the things the way that we are and how we're going to use the things that we define. And this is going to be an introduction to someone who wants to study quantum mechanics at a graduate level and really gain a deeper understanding of quantum mechanics. So we're going to be moving away from a wave function framework and much more towards an abstract definition and representation of things. Okay, so let's start with the big picture of what we're actually studying in quantum mechanics. So we have a system, and the system can be anything. It can be a ball, it can be a table, it can be a particle. And a lot of times in quantum mechanics, it's going to be a particle, right? And this is the thing that we're studying. If we're studying this system, then what do we do with the system? We can ask questions about it, right? So let's ask a question about this system. A question. Now these questions can be anything. It can be if it's a ball, if the system is a ball, then your question can be, is the ball red? If your system is a particle, then you can ask, what is the momentum? What is the position? Is the particle spin up? Is the particle spin down, right? We have all sorts of questions that we can ask about a given system. Now, with a question, we have associated answers. And what we would be interested in is knowing what are all the possible answers associated with a given question. What are the probabilities of all of those answers? And let's say I ask that question on a bunch of different systems, then what's the average answer that I would get? So people who have studied quantum mechanics before probably know the things that I'm alluding towards, but we're not going to jump too far ahead, and I really want to build everything from the total beginning formally, and that's going to lead us to have a much deeper understanding of quantum mechanics. So let's start with the most central thing and the central definition in quantum mechanics. A system's state is represented by a ket. When we write a ket psi like this in a Hilbert space. Okay, so we've drawn our first analogy here. The system state is represented by a ket psi. And what this is, it's some sort of abstract object that we have that holds all the information about the system state. It's some sort of vector that lives in a Hilbert space. So it's a vector that lives in a vector space that has an inner product defined. And let's go on a little mathematical aside to establish some things that we're going to need later on. So first, we have our ket psi. And I said we want to think of this like a vector, right? And we want to think of this like a column vector. This can be an infinite dimensional column vector. It could be a finite dimensional column vector. Now we define another object, which we call a bra. And it's a mirror image of a ket. It looks like this. And if our ket is just the vector v, then our bra is that vector, and we take the adjoint of that. If you remember from your linear algebra what the adjoint is, it is the complex conjugate transpose of the vector. So if we had a column vector before, then now we have a row vector where all of the entries are complex conjugated. Okay, we have these two objects. If we put them together, we do bra and then a ket like this. What do we make? We make a bracket, right? So that's the reasoning for the why it's named this way. So when you put them together, you make a bracket. So this is called Dirac notation. And if you put them together, you make an inner product. This is an inner product. So this is equal to the vector adjoint times the vector, right? This is the bra on the left, ket on the right. So this is a row vector times a column vector. If we do a row vector times a column vector, then it's the sum of multiplying all of the entries, right? And let's remember to put the complex conjugate on the left entry, right? All the entries on the left are complex conjugated. So what does this result in? This results in a real number, right? This is some real number. Okay, so this is what our inner product is. Let's remember. Now we can define a new sort of operation, and this is something that a lot of people who've taken linear algebra actually haven't been exposed to. We can do a ket and then a bra. This is called an outer product instead of an inner product. So we have the vector and then the vector adjoint. So this is like a column vector times a row vector. So if we did a row vector times a column vector and we got a number, what happens when we do a column vector times a row vector? What do we get? We get a matrix. We get some sort of matrix. And in quantum mechanics, matrices are representations of operators. So let's put a hat on this. That's how we say it's an operator. And this moves us perfectly to our next analogy that we're going to draw. We drew an analogy that we represent a system state with a ket. We represent these questions with operators. Okay, so let's say our question is, what is the value of A of the system? We have some abstract observable quantity that and we want to know what's the value of A in our system, right? A can be anything. Now, this question is represented by an operator, capital A, and we put a hat on it. This is what represents our question, the operator. Okay? So let's talk about operators a little bit. Operator A. Now, A acting on some kets A sub I is equal to some number AI. This is some number AI times the ket, same ket back. This probably looks familiar. This is an eigenvalue equation, right? We have the operator with the operator, and then these are eigenkets that are associated with that operator. And associated with that operator, we also have eigenvalues. Okay. Eigenkets are just states. Again, right, kets are just states. Eigenvalues are going to lead us to our last thing that we're drawing a connection to that overall analogy that we made on the top. The eigenvalues are the answers to our questions, right? They're the things that we actually observe. We're asking a question of what's the A value? That question is represented by the operator A. The answers to that question are represented by the possible answers that we can get to that question are the eigenvalues AI. Right? Those are all the possible answers that we can get. Okay. Now, in quantum mechanics, we say that every observable is associated with a Hermitian operator. Okay, so we're saying that all the operators are Hermitian. That's something we can always assume in quantum mechanics. So, Hermitian, what does that mean? The definition of Hermitian is if the operator is equal to the transpose. I mean the adjoint, right? This is the complex conjugate transpose, this is the adjoint. Okay, so in linear algebra, there are some common theorems that you can immediately derive, right? It might be good practice to work through that again. And actually, it's actually great practice to work through these, deriving these two. So it's going to be two theorems. It's great practice to work through deriving these two theorems, not with a common notation that you would use in linear algebra, but with the notation that we're using here, with a Dirac notation. So you should work through proving these. So number one is the eigenvalues are real. If the operator is Hermitian, then the eigenvalues are real. So AI is equal to AI star, the complex conjugate, for every I. Okay, so why does this make sense? Is that we're saying that if all the operators are Hermitian, this is what we ask our questions with, and the answers are the eigenvalues, then we can only get answers that are real numbers. Doesn't that make a lot of sense? It wouldn't make sense if our eigenvalues can be complex numbers. We can ask, what's the position of this particle? It's a complex number. That doesn't make sense, right? The answers have to be real numbers. So this is great. This is a great part of our formalism. Next is if we take the inner product of AI and AJ, and this is 0, right? These two eigenkets are orthogonal if AI is not equal to AJ. So if these two eigenkets are associated with different eigenvalues, then they're orthogonal. Okay. So what does this lead us to? This leads us to a key statement that eigenkets, let's actually bring this down here, that eigenkets of a Hermitian operator form an orthonormal eigenbasis. So what we're saying is that we can form with the eigenkets that are associated with any Hermitian operator, any observable basically, whatever question that we want to ask about a system. Let's say that question is capital A, then that question has associated eigenkets with it, right? That operator has associated eigenkets with it, and those eigenkets form the orthonormal eigenbasis. So if those eigenkets form an orthonormal eigenbasis, right, that's some eigenbasis that spans the entire Hilbert space, then what we have is that we can take our original abstract state of the system, psi, remember, that's what we represent our system as, psi, and we can expand it as a linear combination in that eigenbasis. So if our eigenbasis that we want to expand it in is for the A operator's eigenbasis, then we're going to use the eigenkets AI, right? So it's some linear combination over these eigenkets AI. And this is true for any state. Okay. So what we're saying here is that this overall state, psi, the overall state of the system, can be expanded like this, where we have some coefficient C1, A1, plus C2, A2, plus C3, A3, plus dot, dot, dot. So basically what we're saying is that this system can be some superposition of all of these eigenkets. So it can be a little bit of A1, it can be a little bit of A2, right? It's some mixture of all of them. So let's take a thought experiment of, let's say that all the coefficients, all the C values are 0, except for the first one, except for C1. So we're keeping this one. What happens if we do that? Then psi is just all in that eigenstate A1, so it's equal to C1 A1, and if we're normalizing this, then that C1 just becomes 1, so it's equal to A1. So if psi is equal to A1, this is the simplest case of answering our question. All of the state psi is in the eigenstate A1, so when we ask our question capital A on psi, then what answer do we get back? We only have one answer that we can get back, which is A1 psi, right? Because we can replace psi with the eigenket. Let me just write that. We can replace psi with the eigenket A1. We know it's in that eigenket A1, so we know the eigenvalue has to be A1. So we know the value of A is A1, right? We know the answer. So that's the simplest case. So let's erase all that. But in reality, it's a mixture of different things. And you would think if this C1 coefficient, let's say the C1 coefficient is a lot bigger than the C2 coefficient, or vice versa, right? Then if the C1 coefficient is much bigger than the C2 coefficient, then what we would expect is that when we measure this or try to observe and answer this question, we would expect that we're much more likely to get an answer of A1 for the eigenvalue rather than an answer of A2, right? So we expect that these coefficients play a role in the probability of observing of getting a certain answer, okay? So this actually is the direct interpretation of this. So we have that CI, absolute value squared. So what is that? That's CI star times CI. This is the probability that the state psi is in state AI. Okay. This is the same thing as saying this is the probability of observing AI as your eigenvalue, or saying that being in the state AI, right? Those are equivalent things. Okay, so let's do something of getting an expression for what these coefficients in the front are going to be, right? These coefficients, obviously, we're starting to see that they play a very crucial role in quantum mechanics. There are probabilities, and probabilities, as many of you know, are the central thing that we're studying in quantum mechanics. So let's multiply this whole expression that we have up here, this expression. Let's apply a bra on the left of this expression. Let's apply the bra AJ psi. Then what happens is that we can just take the numbers out into the front, right? CI's are just numbers. And then we put the AJ that we just applied on both sides of the equation. And then the AI, that's the last thing left over. Okay. So we said that the eigenkets form an orthonormal eigenbasis. So if they're orthonormal, then this inner product that we have right here, this inner product of AJ and AI, this is going to be 0 for all cases, except for when I is equal to J. And when I is equal to J, it's going to be equal to 1, because we said it's orthonormal. So what is this represented by? This is represented by what we call a Dirac delta. So the sum over I, CI, Dirac delta, IJ. Dirac delta is just a value. It's just a function that is equal to 1 when I is equal to J. It's equal to 0 when I is not equal to J. Okay, so what do we get? We sum over all those possible I values, but everything is 0. It's only not 0 when I is equal to J, and when I is equal to, let's get rid of summation, so we only get one value. When I is equal to J, we get CJ times 1, right? The Dirac delta becomes 1 at that point. Okay, so we just found an expression for what the coefficients are, because we found that CJ is equal to AJ, right? CJ is equal to AJ times the ket psi, right? The bra AJ times the ket psi. So we can replace those J's with I's, right? If we want an expression for CI. Okay, so let's do that. Let's start with this. Let's rewrite this expression up here again, right? This expression that we have. Psi, the ket psi, is equal to a sum over I. And let's put our AI first, right? We have an AI up there. And now we have the coefficient CI. It's just a number, so we can move that around. We're moving it over to the right. And our coefficient CI, from what we just derived, is going to be AI times psi. Okay. Now, is there anything interesting that we noticed about this expression that we just derived here? This is something that's very, very crucial part of quantum mechanics, and especially when you're studying more formal and mathematical quantum mechanics, is that we have a psi here, we have a ket here, then we have the same ket here, and didn't we just say that that this we have an outer product over here, right? We have this outer product with a sum of outer products. And we said that outer products are operators. So we have a sum of operators, which is an operator. So we have a ket, some sort of operator, and then the same ket back. Then obviously that operator has to be the identity operator, right? So we have the identity operator is equal to the sum over the outer product of eigenkets. This is a really central and a crucial result in quantum mechanics, and it's something that's very important to understand. And let's dive deeper into getting like an intuition of what this even means. That we sum over an outer product of all of those eigenkets, we get the identity. Why is that? Let's build that intuition right now. Okay. Firstly, one thing I want to emphasize is that it doesn't matter what the eigenkets are. It's just any eigenbasis, right? We can be asking the question of what's the b value. Then the identity operator is also a sum over the b eigenkets, right? So we're asking a question with the b operator, right? This is the same thing. So we can expand our ket, our eigenket. We can expand our ket of the state in terms of any eigenbasis, any set of eigenkets. So for any observable or any question that you're asking, you would have a different expansion. So going back to this expansion here, that you'd have some different expansion, you would have some different coefficients, right? Wouldn't that make sense? You wouldn't have the same coefficients if you're asking for what the a value is versus if you're asking what the b value is. There's different probabilities of having a value of a1, like a value of a momentum 1, or a position 1, right? So that makes sense. Okay, let's develop some intuition here. Let's say that the Hilbert space that we're working in is just our three-dimensional space that we're familiar with. So we have some three-dimensional space. And our ket that represents our state lives randomly in here, right? Points in any direction. It's in some superposition of the different states. We can have, and let's say the question that we're asking is the position, right? The position. So we would have 3 eigenkets of position, which are x1, x2, x3, right? Our eigenkets associated with different eigenvalues are going to be orthogonal. We can see visually these are orthogonal. So this is like our x, y, and z. These are orthogonal. So what we can do is, as always, we expand our we expand our ket of the state in terms of the eigenkets. So with some coefficient of x1, we have some amount of x1, right? It's pointing in the x1 direction, some amount, plus some amount of x2, plus some amount of x3, right? That makes sense. This is just how we have three-dimensional vectors. Okay. Now let's develop an intuition of what the outer product even is. I know it's a mistake here. Should be like that. Okay. Let's build an intuition of what the outer product even is. Let's do an outer product operation on this ket psi. Let's do an outer product operation on the x1 eigenket. And let's apply this operator onto our state psi. If we apply this operator onto our state psi, then what happens? We get, we can just bring the number out to the front here, and then we get x1, and then what do we have left? We have just x1. Okay, plus c2. We have the x1 that we're applying, this operator, then we have an x2. Then c3, x1, x3. Okay, now let's simplify this. x1, this is going to give us 1, right? Inner product with itself, orthonormalized, it's 1. These are two different eigenkets. Inner product of those is 0 because they're orthogonal. Two different eigenkets. Inner product of those is 0. All those terms go to 0. This one becomes 1. So what we just did was, by applying an x1 outer product onto our state ket, we just get back c1, x1. We just get back the portion of the state that's in the x1 direction. So what did we just do? We did a projection operator. That's what I've been avoiding saying from before. But what an outer product is it builds a projection operator. So what we just did was, by applying this x1 outer product, is that we projected the state psi onto the eigenstate x1. And we figure it out, and from that we get the coefficient. We get this, right? We got c1, x1, like how much of it is in the x1 direction. We got some projection. So if we do a projection, okay, so let's do, so now let's figure out why is this the identity operator, right? So the identity operator is equal to, let me just do the state psi is equal to a sum over xi, and then psi, right? This is what we just had discovered before. And this is literally this equation expanding. That's all that this equation is. It's expanding our state in terms of the set of eigenkets associated with some certain operator, some observable. Okay. And we applied, what we did was we applied this identity, right? So why is this the identity? If we project the x1 projection, we get this arrow. If we then project in the x2 direction, we get some portion of it that's in the x2. We get c2, x2. And then we project in the x3 direction, we do the x3 outer product. We get the portion of it that's projected onto the x3 eigenket. And it's the summation. So we add all those back up together. If you're adding the portion of it that's in the x1 direction and the portion of it that's in the x2 direction and a portion of it that's in the x3 direction, what you get back all together is the vector that you started with in the beginning. Like, this is why it's an identity operator. You're projecting in every direction in a complete eigenbasis. So this is why it's an identity operator. Okay. So now I think we built up a good intuition of what these projections are. These projections are crucial because here's the central thing. Now we're going to move towards some of the big things of quantum mechanics to understand. Is that measurement, right? We've been kind of avoiding the talk of measurement. Is that measurement is equal to AI for some I. Okay, measurement is equal to an outer product for some eigenket. It's projecting you measurement projects you onto some eigenket. Measurement is a projection operator onto an eigenket of the operator that you're asking about. So let's make a new image, right? We had this analogy that we worked at the total top of this page here before. Let's make a new image that we're gonna that we can establish what measurement really is. So we have our system that we study, and this system is represented by some ket psi, and we want to take a measurement, right? We have a certain question, right? We still have that question. We still did our overall theoretical stuff. Like before, this line of thinking that we did before was like the purely theoretical. Let's say like before I'm actually gonna go into the lab, I'm gonna actually test anything out. Like I'm just thinking on a piece of paper what's happening. And with that thinking, we established like a question with an operator, right? Remember all that from not too long ago. We had a question with an operator A. Now we want to actually measure, like, what's the value of A? When we do a measurement, what we're literally doing to this system is applying, let me put that in blue. What this measurement literally is applying a projection operator onto our ket. And what that does is we apply this measurement operator onto our ket, and we get some certain eigenvalue back. Right? We observe, we measure some eigenvalue of the system. What this does is this collapses the state. So now the state of the system is literally just it's just this eigenstate. It's just this eigenket of the operator A. Whichever one you observed. We have probabilities of which one you're going to measure and which state you're going to collapse onto. But we don't know for sure, right? The measurement is just, remember I said it's for some I. We don't know for sure. We can't tell you exactly what state we're going to collapse onto, right? This isn't quantum mechanics isn't a deterministic science. It's not like classical mechanics where I can tell you exactly where this particle is going to be using F equals ma. I have the trajectory of the particle. No, I'm going to give you probabilities of what your measurement is going to give you, but and tell you what happens after you do that measurement, which is the collapse of the state and the state collapsing. So given, let's say I measure the AI, the ith eigenvalue. Let's say I measure A2 as the value, then what I just did was apply an A2 outer product. And what that does is that I projected the system onto the state A2. Right? That's what I did. Okay. So remember we said with this measurement side, we have a probability that it's going to be the AI, the AI projection that we do. This is going to be equal to the CI coefficient squared. Remember that. And remember we found what that coefficient was. It's the AI bra times the state psi. And so it's going to be this thing squared. Absolute value of this thing squared. So now let's introduce the idea, and this is going to be the last thing that we do, that introduce the idea of an expectation value. An expectation value is what's going to happen is if we set up a bunch of these identical systems, and I'm going to be asking the same question on all those systems, and what's the average answer that I'm going to get? What's the average value that I'm going to get for that answer? Note that this isn't the same, and this is a common misconception, isn't the same of having one system, asking the question, and asking the question again on that same system, because you're going to get the same answer, right? What's the energy? And then you ask, and then you get the value of the energy, and you ask it again. You collapse the state. Remember, you did a measurement, You did a projection operator. You should be visualizing it like this here. You just projected. You're asking how much of it is it in the x1 direction? Okay, you did that measurement. You collapsed it in the x1 direction. You collapsed it in the x1 direction. Then you ask again, you're going to get the same answer, right? So the key thing here is that for expectation values, this is what an expectation value is, the average value. So that you want to, like, what the analogy is having a bunch of different systems, a bunch of identical systems set up together. Okay, so an expectation value for A is the average value of the observable A. It's a sum over our probabilities, which are AI psi absolute value squared, times the answer that you can get. It's a sum over those. So this is like a weighted sum, where over here we have our probability. So we have the answers that we can get, and it's that answer times the probability of that answer. So it's weighted by a probability and a sum over all those answers. So this is like a weighted sum of our values. So this is what an expectation value is. Okay, so this is equal to an absolute value squared of something is just equal to that thing complex conjugate, and then it times itself, and AI, right? We're taking it's the complex conjugate times itself, and then for an inner product, remember that the complex conjugate of inner product is that you can just switch the order of the inner product and get rid of the complex conjugate. This is something that would be introduced to you in a linear algebra class. Okay, and now we have this expression, and now this AI that we have on the end here, it is just it's just a number. Remember we said it's just a real number? So we can move this anywhere we want, and so let's move it over here. So then this is equal to the sum over I psi AI, a number, AI, the eigenket, AI, eigen bra, not that usual terminology. We would still just say eigenket, right? And then psi ket. Okay. Now we have over here, we have AI eigenvalue times AI eigenket. This is the same as the operator A on the eigenket, right? That's using our eigenvalue equation. That's always true. And then AI psi ket. Okay. Now, last thing, notice that we have now our summation is over I, and we only have I in this one spot over here. This outer product of over eigenkets, AI. And this is a sum over I of outer products AI. That is just, hopefully we remember, the super crucial thing that I emphasize a lot. That is our identity operator. So that is just going to disappear. This is just an identity. And the sum would disappear too, right? Psi A psi. Now this is what we would recognize from someone who had taken some quantum mechanics before. They would recognize this expression for an expectation value. But I feel that we got there with a much more deep intuitive understanding than before. Okay, I hope this helped. Later we might move on to some, we might dive into this a bit deeper, introduce some concepts, Fourier transform, and as well as continuous variables, right? We've kind of only been talking about like discrete quantities right now, and also how time dependence fits into this. All right, thank you.